There normally breaks that seem to be well placed. I'm not sure what happens, but it's been weird. So here we are. That's okay. We were talking, well, about this, right? Nobody clean the board. We were talking about Faraday's law and Lenz's law and motional EMFs, which are, Faraday's law, remember, is not here. Faraday's law says this. An induced EMF is equal to minus N dphi dt, where this is the magnetic flux. N is the number of turns in some coil. It could be 1, it could be 6 million, large coil. But the idea is if you have a closed loop of conducting material, something that can carry a current, you will induce an EMF, and you have a magnetic flux through that loop that's changing. That's the important thing. Magnetic fluxes are fine. Changing magnetic fluxes cause this issue. If you have a changing magnetic flux through that loop, and this is the number of loops you have, an EMF is induced. When what is an EMF? But a potential difference, right? It's an electric potential or voltage, if you will. But an EMF is induced such that current flows, if possible, in a way to counteract the change in flux, or to attempt to counteract the change in flux. It doesn't ever actually completely counteract it. But we're going to look at some situations today where it has some practical ramifications for that. So all those qualities have to be present. There has to be a magnetic flux through the loop. It has to be conducting material. Then there has to be a magnetic flux through the loop of conducting material. It has to be a changing magnetic flux. And then, if that's the case, the EMF is induced. The negative sign, if you remember, just goes to, the meaning of it is that this EMF is induced in such a way to oppose the change. Routinely in my class, I had this discussion with a student earlier today, in my class I typically ignore it because practically the reason you need it is to determine the direction of the current flow. We're going to do that with other means. The right-hand rule, it is possibly to rigorously determine the direction based on the negative sign, as long as you understand what your conventions are as far as what's positive and negative. But I don't do it, and most of us don't. That's not to say that your future instructors or professors will just throw it away so easily. So you need to know it's there. You need to know why it's there. Practically in this class, we tend to not worry about it. My example was if I ask for an induced EMF from this coil and this changing magnetic field, and by this the answer is negative 100 volts, and you just tell me 100 volts, that's okay with me. Because then the next question I'm going to ask you is which direction does the current flow, right? Which is the whole point of the negative sign as it is. Know what it means. It means that the EMF is oppositional to the background field. But I tend to not worry about it when we're calculating. The other thing I'll say about this is your book uses some language that I find strange. It talks about counterclockwise EMFs or clockwise EMFs. An EMF is non-directional, right? Voltage is not a vector. What they mean, of course, is an EMF such that a counterclockwise current is produced. And that's probably somewhat obnoxious to say, so they'll just say counterclockwise EMF. The language is weird, right? There is no such thing as a directional EMF. A battery is not, north or south, center. That doesn't make any sense, right? But that's what they mean when you see that. The EMF is not directional. The current it can produce is directional. So that's all I'll say. Okay, so we're going to talk a little bit about back EMFs today, and we finished up the discussion last time by talking about generators. Right? The idea is, in accordance with Faraday's law, if you take a coil of wire and you put it in a magnetic field and you rotate it, you don't have to rotate it, but in this case you do rotate it, what that produces is a change in flux through that coil. Remember what the flux is. It's E dot A, where A is the area vector of whatever the coil is. But if I unpack that, That's BA cosine theta. Alright? So this tells you the three ways the flux can change. The field can change, the area can change, and we've seen examples of both of those, or the orientation can change. And this is practically speaking the way we always do it, right? I mean, not always, but practically speaking, this is the easiest thing to change because physically you can construct a coil that's connected to some sort of armature that lets you rotate it, stick that coil in a magnetic field and spin it around. That changes the angle, right? And then we went from there to figure out that if I then take the derivative of this with respect to time, what is changing with respect to time? Omega. What we had also said is this is rotating with an angular velocity, omega. And which is, of course, the time rate of change, not theta, yes theta, but not what I wrote phi. Theta, right? Time rate of change of the angle. So that's the angular velocity. If I'm rotating this thing with some omega, if I take the time derivative of this, B and A are not dependent on time. Theta is, therefore cosine of theta is. I get B, A, and then derivative of the cosine is the sine, it's the negative sign, but I've already said I'm not going to worry about negatives. So sine, again, that doesn't mean your future teachers will not worry about negatives, so you need to understand that it's there. And then by the chain rule, since theta itself is a function of time, not only do I take the derivative of the sine of theta, I take the derivative of theta. I get d theta dt, which is just omega, which leads us to the idea that d phi dt is I can write as b a omega sine theta, but we typically write theta a little differently, recognizing that I can express theta, if you just look at that equation there, in terms of omega and however long you've been measuring it. So the typical way we write this is omega t. That's theta. So this is the equation we came up with. Stay with. Oh, sorry, I thought there was a question. So this is the equation we came up with once I took the derivative of the flux. So then, of course, if I want the EMF, all I really have to do is add an n. Again, I'm not worried about any negative signs. Turns out the negative signs in this case, if I'd kept them in, would end up canceling anyway, because I have a negative from the definition, a negative from the derivative of the cosine, that would go away anyway. But I'm not worried about it. Okay, so this is the EMF induced in a coil when you rotate it inside a static magnetic field. Alright, so notice it depends upon the angular velocity. Right? Of course it does. So the angular velocity, as I've derived it, we assumed pretty much that it was constant. But it doesn't have to be. So think about the last time you turned on something with an electric motor. Maybe you could see the motor, maybe you couldn't. But nothing in this universe happens instantaneously, at least not mechanically. Talk about quantum if you want to, talk about instantaneous things, but mechanically nothing happens instantaneously. So when you turn on a motor, there's a ramp up time, right? If you turn on a vacuum cleaner, it takes a little bit of time, very little bit of time, to ramp up to its final speed. If you've ever done any machine work with a grinder, like if you turn on your grinder wheel, it starts to rotate faster and faster. Then when you turn it off, it usually takes a long time to slow down. My chop saw that I use at home when I'm doing projects, right? It has an electronic brake which doesn't always engage when I let go of the handle. So if the brake engages, it grinds down to a halt really quickly. If it doesn't engage, it sits there and spins for about 30 seconds while it slowly comes to a halt. The same thing happens the other way. When I turn it on, it spins up, right? So these things take time. So let's ask ourselves a question. If I have some sort of system which I will represent like this, to leave a gap there on purpose, where this resistor there are symbols for motors, which I'm not going to worry about. And we're just going to consider speed as a big resistance. So the point of this is not the resistance, though, right? The point of this is to ask ourselves, what happens when I turn this motor on? Okay, so I flip a switch, and notice I've left a gap here that I'm going to fill in a second. I flip a switch for my EMF, my source EMF, and this motor starts to spin. Well, what has now happened is I have a coil of wire that's spinning in a magnetic field. I mean, it's spinning in a magnetic field because I made it, right? I connected it to the EMF. I input electricity to this thing, which is not the same thing as, but also means I'm inputting energy into my motor. And it starts to spin. But how does a motor work? Well, you built one last week. You've seen it, right? You have a current that's flowing through a coil that's in a magnetic field, right? And if you orient it correctly, it's going to start to spin. Well, now I have a coil that's spinning in a magnetic field. So Faraday's law says that I'm going to further induce an EMF in the coil. This is a different EMF than this guy, right? This is my source EMF. It's a battery if I have a small motor. It's my wall if I have some sort of transformer to run a big motor. But I have a source EMF. That doesn't change, of course. We'll say this is E source. It's constant EMF. So I start to spin the motor, and thereby I induce another EMF that seeks to oppose the change. What does that mean, seeks to oppose the change? It might look something like this. What have I done? I've drawn a battery wired in opposition to my other battery. Whether or not it's an actual battery is immaterial. Well, this one's definitely not an actual battery. This is my induced EMF. Whether or not this is an actual battery is immaterial. The point is, this battery is trying, and I should say succeeding, in pushing current. I have another color. Maybe not. We're going to chalk it. They didn't clean the board, they cleaned the chalk. I'm pushing a current this way, right? This tries to push a current the other way, but it doesn't succeed because my motor still turns. That doesn't mean this is not a thing, right? So I have this source EMF, and just by virtue of spinning this motor, I induce what's called a back EMF, right, that seeks to oppose it. Now, this is interesting because this back EMF is this guy right here. This is what's induced. My source EMF is static, but this is a function of time. Because when I first start to spin the motor, like as soon as I turn it on, I should say, before the motor has started to spin, what's the back EMF? 0. What's omega before the motor has started to spin? Well, the angular velocity is 0 if it's not spinning. So the back EMF is 0. Okay. Well, as the thing starts to spin up, notice that the back EMF starts to increase. So there's greater opposition to the motor spinning in the first place. This will reach what we call a steady state when, I'll show it like this. It will eventually come into an equilibrium where I have current flowing, but my back EMF has come to a stable position, right? And here's what happens to the current when that goes on. Think about this in terms of the total EMF. The total EMF here. I'll do this. Minus E induced. I wired it backwards. This is an oppositional EMF. Sometimes you'll see this written with a plus sign here. What they're saying, of course, is that this quantity itself is negative, right? I'm not going to do that. What we're saying is the total EMF is the source minus the induced, Okay, but the induced is what changes as the thing starts to spin up. Think of what this does from the point of view of the current. Because we have Ohm's law still in effect here. V is equal to IR, therefore I is equal to V over R. But what is my voltage in this case but the total EMF? So instead of writing V, I'm going to write this. E source minus E induced over R. And what we're saying is this quantity changes. Right when you flip the switch, this is 0, which means my total voltage is the E source. Right? So that's a larger voltage than it's going to be eventually. So that means right when I flip the motor, it draws a lot of current. There's just a ton of it flowing through there. But as the thing starts to spin up and the E induced gets bigger and bigger and bigger, in other words, as omega itself gets bigger and bigger and bigger, I start to draw less and less current. This is why I mentioned last time, some of you that grew up in older houses, like the house I live in now was born in 1950. The electricity has mostly been redone, so we don't see this happen a lot. But I remember really specifically being in my grandparents' house when I was a kid, and when she would turn on the vacuum cleaner, or the dryer would kick on, or a hair dryer would come on, the lights would dim. And this is why. Because when you first turn on that motor, you draw a heck of a lot of current. There's only a certain amount of current that can flow into your house. So to get that amount of current, you have to take it from somewhere else, which is why the lights dim immediately when you turn on that motor. But as the thing spins up and the E induced starts to get higher and higher and higher, the total EMF comes down and you draw less and less current. Right? Typical way that these things are asked, let me find an example. We'll do it. Should have had this ready. Here we go. Sorry, 2 seconds. I thought I was there. Turns out. All right. So usually you'll see questions like this that will run something like, well, first of all, any questions about this? What was that? Okay. First question, we'll ask another one. Motor has a total resistance, that's a capital R, 200 ohms. When you first turn it on, it draws 40 amps of current, and then 5 amps after it is at speed. I have to put my spaces more carefully. There we go. What is the source EMF? First question, what's the source EMF? Very simple Ohm's law problem. So what we have said now is that Ohm's law, instead of writing just V for voltage, I need my total EMF here. It is the total voltage, but my total EMF, which is E induced, E source minus E induced to IR. So that's my equation that's describing this. All right. If I draw 40 amps of current right when I turn it on, what is the induced EMF right when I turn it on? 0. Why? Motor's not spinning yet, right? The back EMF is a function of the speed of the motor. Very good. And until that ramps up, I expect it to change. But right when I turn it on, E induced, in this case, turns out to be 0. So I just reduces to E equal to IR. So what's my source EMF? Well, in this case, it's going to be 40 amps times 200 ohms. It's going to go at 8,000 volts. So 8 kilovolts, if you will. Now, next question. What is the back EMF at speed? I think this is pretty straightforward. Any questions about how we got that? Alright. What's the back EMF at speed? Well, and now that I'm up to speed, that is no longer 0. But now I know what the source is. I know my new current, and the resistance hasn't changed. So I can now write this. E induced is going to be E source minus IR. Just rearrange things. So I found that my E source is 8,000 volts minus, what's my current speed? 5 amps times 200 ohms of resistance. It's going to be what, 7,000 volts? 5 times 200 is going to give me 1,000. 8,000 minus 1,000. If I did the algebra right, I get 7,000 volts. Back EMF. That is, at least that difference is somewhat typical. You'll find lots of systems that'll draw 95 amps of current right when you turn them on, but they're operating